Alright, in part 2, we'll get into datum feature symbols. And let's take a look at what kind of symbol that we use for datum feature. Okay, so here this is your datum feature symbol, right? So when you take a look at the symbol, we have a particular angle right there. See that little angle right there? And that's 60 degree, and then your height from here to there, yes? And then from here to here, you can use any appropriate height, okay? This one, sometimes you're gonna have a specific or a height for it, okay? In your drawing, so you have to pay attention to the height of the letter and the height of this little box, and then the width of that, okay? So that's got to be 2 times of this, and this got to be 2 times of that, okay? So that's how we're gonna write the datum feature symbol. And if you use a CAD program of some sort, yeah, it's completely defaulted, yeah, so you don't have to do anything about it. So anyway, so here we go again. Yes, this is just trying to reiterate everything that I have just told you about this feature. Yeah, you pay attention to the height. You can just like draw height, like h for the letter like this, and then like shoot out like 4 times of that. You can do that. Yeah, it's from here to here got to be 2h. Yes, in dimension, of course. Here got to be the same thing, meaning like it's a square. Yeah, your rectangle, triangle got to be 60 degree for your angle. From the horizontal line to this hand is going to be 60 degree. The height again is the same as this letter height. And then from here to the box, triangle to the box, you can do any appropriate length, but don't do it like so, like so tall or very long. Just keep it, reasonable height right there. Yeah, that's what it's talking about. Of course, don't use the alphabet I, O, and Q. You can use all other letters, but we keep it simple A, B, C, D most of the time, yeah, for the datum. All right, here are your examples for different orientation. You can write or put it that way. Different letters right here, C, I, O, Q, you don't use it because a different angle right there, we put it, yeah. All right. And then angle meaning I know the triangle angle, yeah, the angle of how the triangle is standing, yes, 90 degree or a particular degree. This is 180, that's a 270. Okay, datum feature symbols right here. You can attach, you can apply to the related surface in this way. So related surface is here, 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 and here, yeah. So you can put it on a feature surface outline, extension line, dimension line, and also the feature control frame, yeah. So let's take a look at, so here is your datum feature symbol, yeah. So here we stick it here on this surface, we stick it here on the extension line right there, yeah. Also here an extension line, yeah. So we have our datum A, B, and C, yeah. Okay, the next one, we're gonna stick our datum A, yes, right here on this extension line of this feature size right there, yeah. And then of course there's in this example you have your diameter symbol because you're dealing with a cylinder right here, yeah, from the front view. And here, yeah, since you're dealing with a cylinder of diameter that size and your datum is going to be A, and that datum feature symbol is right here, stick to this extension line, you have to deal with this axis, yeah? So here in this case, the axis, so here you can see the center line right there, see that? So the axis of gauge, and you're going to measure the axis of that feature, yeah? So this datum is trying to make you be aware of this, okay, and be careful with this dimension. So the actual, since you have a diameter right here, look at this, yeah, so actual datum feature is actually, we're dealing with this diameter, but as you know, diameter is a circle, yeah, dimension. So therefore, there is the center of that circle, which is your axis. So you still have to deal with the resulting datum, which is the axis of that gauge, yeah. That's what it is talking about, yeah. So if I have to simplify that for you, so if you see a datum connected to the diameter, just you understand you're dealing with the diameter and the axis right there, yeah. That's what you need to know. Okay, let's go into the next one. So if you don't have enough space, of course, yeah, we're gonna do a shortened it, which is this guy, yeah. And I already told you that how to shorten if you don't have enough space to put. Yeah, so we're gonna shorten it, and then here's the axis for this hole going into it with a depth inside of this part, and then here's your datum feature symbol right there, and of course you're dealing with something here. Okay, so all of them here, each of the example is dealing with, when you look at it, see axis, 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 and axis. So therefore, the datum feature is gonna have control on the axis, or the center of the plane. Datum feature right there, here, and then here. We just call it, datum feature A, and then B right there. Associated, symbol right there, diameter, and here we're dealing with the x. All right, and then another one. I'm just looking at who is drilling something. I should go and close the window one moment. Here is another example here. You see the filled triangle. Here is unfilled, white diagram. Here's black right here. So this is just a filled and unfilled triangle for your different ways of designating your datums. We have datum E and D. We just stick it onto the circumference of this circle, and here also. So we use the arrowhead right there from here to here. So just showing you the dimension of this circle diameter. Dealing with this. Look at this, the diameter. So here and filled. See this little arrowheads right there, two of them, and here filled. It just go from the surface, circumference, which is the base of this filled, triangle of your datum feature control right there, and go all the way down to here. See, there's only one arrowhead. So pay attention to these little things when you draw. Here, going back to the previous example, here just a regular, right here, extension line, dimension line in, yes, dimension out. Okay, so many different ways of putting the symbol into the dimensions. All right, here we go with a leader line right there. Feature control frame, the whole thing is right here. That's associated with this feature, of course. And then you have all information, and here is the A, B, and C. Your datum feature symbol. You can also put it to the feature control frame like that, by the way. It's just telling you that this datum feature D is associated with this diameter of this, hole right here in this part. And tolerance is going to be right there, Because when you pay attention, your brain is going to start thinking and get confusion. That's your lower limit, and that's your upper limit, You don't have the value dimension. So that's another way of writing tolerance. So you know that you're giving a tolerance range. Here it's just giving you the tolerance plus or minus a 0.1. So you have no idea where the medium, the midpoint is going to be. So just don't worry about it, because this is for the entire thing. That is only for this diameter right here. I don't want you to overthink and start thinking, relating that to, they're not related. Right now, just concentrate. You can put the datum feature symbol right on the feature control frame like this. That's all you need to know for now. I gotta mention this because there are like students who think like that, and they're always wasting time for no reason. Then we'll get into your handout number 7. Datum. I put the number for you so you can trace datum targets. All right. So datum targets is gonna point out elements in your object. So when you have like a complex elements on an object, you have like a curve or bold or rough surfaces, then we'll have to use a datum target. Because we do a lot of manufacturing, yes, a process like castings or forging, things like that in the manufacturing. When you apply, yeah, these processes on a part, it's sometimes like difficult, yeah, to align the processes with the flat datum planes. So don't worry about it here yet. All you have to know right now is we use a datum targets. Yeah, datum targets if you have so many elements on your drawing, yeah, of the object. So datum targets, we usually use them to adjust the surface, yeah, to the datum plane. I'll show you, yeah, one by one. You have to visualize it. You can get it by reading it. So datum targets are, we have points, we have lines, and we have area, yeah. So point going this way, line with this, and then the area, of course, with the looks like section lines, yeah. So here, little point with a cross, it's just showing you the angle from here to here for that point is 90. Height is going to be, yeah, 2h. Datum target line look like that, see, with a little 2 dash. And also your datum target area looks like a section, yeah, with a circle right there with the dash here, 2 dashes on each side, so altogether 4, yeah. Be careful with how many dashes we use for each datum targets. Okay, so let's see how we use them. Symbols. These are your datum target. Yeah, this one is your, of course, your diameter right here. Yeah, size is here. Then here is your reference letter, datum reference letter, and then your target number. Yeah, so this is how we're gonna use the datum target information in this symbol. So here, area. We're gonna describe the area like this. Yeah, all the information in here. Diameter 8, yeah, datum A, and then yeah, which is this one, okay, target number. So that's where we relate, okay, to the area, and then the description of that area. So the target, you gotta show it on the side, yeah, of the feature. So we put it on the side of it. Here is your feature, and here is the site. You can't put it right here or right there or right over there. Yeah, let's put it on this side, usually left, yeah, or where the space is, in this example, on this side. And then you're going to connect with the line. Yeah, see, you can't leave this line out. So you have to connect the information with the area. Yeah, target symbol. We don't use arrowhead in the line, just a solid, yeah, plain solid leader line. Alternative symbol. Instead of putting inside, you can take it outside. Yeah, if you don't have space or things like that. All right. Another example here. Yeah. So if you have a target that is associated, yeah, on the far side of the object, then you stir the dash line, yeah. Applications, data target symbol, we put the information in it, yeah. Your point, your line, see? Data target symbol, which is little cross, so therefore we know that's for your point. So we sometimes use it because their data is sometimes points, lines, yeah, or area. So if you use a point, then it's going to establish your datum, yeah. So we can use a point to establish primary, yeah, primary datum. Sometimes we use 2 points for secondary datum and then 1 point for tertiary datum. Application point, we're going to put it into the example like this. So I have 1, 2, 3, A1, 2, and 3. And that's your datum target symbols for the points. And here is my datum right here, another datum C, yeah. So here we have datum target symbol, and this is your datum feature symbol, yeah, for the surface. Same thing here, point, point, yeah, feature, feature, and then point. So here we have primary datum, yeah, because it's A anyway. This one secondary, and that one is your tertiary. Yeah. Then we go into area, the same thing. There's three little area. Primary data because it's A, B, and then C is your feature. A is your feature, and this one is your target. Yeah. B, therefore that's a secondary. Yeah. Target symbol, secondary datum target symbol, and here we have your datum feature. Yeah, which is a line. This is a point, and that's your area. And this is your datum feature. Yeah. B, secondary, and this is your tertiary, which is a line target. All right, then we'll get into the supplementary symbols. So supplementary symbols, we'll put it in a table here. So you can see spherical diameter, we'll write this S, and the diameter radius is R, spherical radius is SR, controlled radius is CR, yeah. Reference is in a bracket, see. Arc limb is a part of your circle, yeah, circumference, like that. And then statistical tolerance, you have your ST, mean S for statistical, and the T for tolerance. And then this is just a line with two arrowheads ends, so that's showing you between, yeah. So except this ST, yeah, all of the standard symbols, they're present, okay. They're presented, all right. They're presented in the unit on dimensioning and tolerance and standards, yeah. Don't worry about it. Just like you gotta pay attention to the symbol and the description, yeah. Just by looking at it, you should know these things with the symbols. All right, then we'll get into our handout 8 on basic dimensions. So when you deal with the dimension, we know that just a value, yeah, and we're gonna describe the size, the profile, orientation, location, yes, the exact size of your feature or your datum target, yeah, datum target. So anyway, if you think about dimension, you're dealing with a value. At least you have to know that, yeah. So we use the dimension to establish your tolerance ranges, of course, yeah. Tolerance plus or minus your dimension value. So here are our basic dimension right there, and standard, yeah. We use like this, your dimension lines with the arrowheads and your extension lines, okay. The same thing, yep. We follow ANSI Y 14.5 M 1966. Of course, some professor is going to make a test really hard by making you remember 1966. I won't do that, yeah. At least if you know, like, we're following standard. Usually ANSI, ESME, yeah. Y something, at least 14.5 you should remember. Then you're okay, yeah. Current standard usually follow the ASME, yeah. And this is another way, and here is the rectangle box that we talked about, yeah, the value in it, and that's your dimension for basic. BSC is another way of writing it. It's just like basic, yeah, BSIC, the same thing. We're just putting the note in it. So we use these dimensions in our drawing, yeah, geometric tolerances. We add to the dimension, yeah, so you know the variation, acceptable variation or permissible variations, yeah. So we use a basic dimension to define your gauge size, location dimensions, yeah, like your datum targets. Then we're gonna apply our tolerances to that dimension that we have, yeah. So you have dimension value and the tolerance range. So if you use this basic dimension, yeah, to define a gauge size or location, what you have to pay attention is like gauge maker's tolerance is going to apply to that basic dimension, and you don't have to do your tolerances, okay, in your drawing. Basic dimension is just a value, yeah, for your size, orientation, profile, or location. Basic dimension usually don't come with the tolerance, yeah, but basic dimension that is going to define your feature size, orientation, profile, or location relationships, yeah, you have to do your geometric tolerance and establish your tolerance zone, of course, your range, yeah. And when you use your basic dimension for gauge size or location, yeah, you don't need tolerances, yeah, because these dimensions for gauge size or location dimension, they're not on the part, okay, that's just a gauge size. So therefore, you don't have to put that tolerance in there for that dimension. Yeah, it's just a value. You won't know it by now, okay? We gotta look into it with a diagram so you can see. All right, additional or bonus tolerance. We usually apply the geometric tolerance, of course, to feature of the size, yeah, feature of size. And we usually use our MMC or LMC, yeah, or FS with it. But when your physical, yeah, size of your feature is way, way away from your MMC, yeah, at that time, your tolerance is allowed to increase, okay? So that depends on your material. And it got to be like that to make sense, yeah? You can just use a fixed one if you have the real or the physical size of your part is going to be away from that, what we have for MMC. So it means that you have to increase your tolerance, yeah, to account for that. And we call that the bonus tolerance, yeah? Meaning like, hey, I can deal with the regular one, I need a bonus, yeah? Because I can make it to that material because it's so far away from your max, yeah? Something like that. So let's see our bonus and tolerance. So here, your feature size is controlled with your geometric, yeah, tolerance, and your tolerance is modified to apply when the feature is at your maximum. Here, see, M is a little bit off. So M with a circle, that's your maximum material condition. And we put the additional, see, material additional tolerance in addition to the regular one, yeah. So the one that I showed you in a previous example, oh, don't worry about it when we put the datum, right? To here, I said, oh, don't worry about it. Yeah, that's because you have like a two different, and of course here you have two different, yeah, tolerance right there. So meaning like you have a bonus tolerance in it, yeah. So like the previous example that I showed you, don't worry about that. And why do we need the bonus tolerance? Again, in order for us to cover, yeah, your material condition when they change. More examples, yeah, bonus tolerance. So you have your at MCC, MMC, the tolerance for center plane straightness, yeah, is going to be 0.2. The thickness size is going to change, yeah, go towards the LMC away from your MMC. So the variation center plane straightness is going to be proportional to that, yeah. So here we're showing, oh, the feature size is 1.3 MMC, the straightness is 0.2, additional tolerance is 0, the combined tolerance is 0.2, okay. And this is where we start off, yeah. So let's see changes in it. So now we're going down, yeah, from 1.3, the upper, yeah, size limit, and we're gonna go down 1.2. Your straightness tolerance 0.2. We're gonna add a tolerance, okay, 0.1, a little more. So combine, you're gonna add the bonus and this 0.3. Yeah, it's not that difficult. 0.2. So you have a combined 0.4 because your additional or bonus is 0.2. when you look at here, 0.4 is your max band right here, yeah? And you can go 1.5 from here to here, yeah? That's your fixed limit for your gauge. Then we go 0.5, yeah, max band, because our bonus is 0.3 right now in addition to our regular 0.2. Yeah, so this is how you can see. So if you have like combined tolerance, you should be able to calculate the added bonus, yeah, tolerance by looking at your regular tolerance given in your control frame right here, yeah. Of course, now we're not at LMC, going all the way down from 1.3 towards a 1.0, yeah, meaning like this is what we're saying, going far away from MMC to LMC, from max to least, okay. Each one of them we go, we have added tolerance to it. So you know that there's a bonus because, see, like I tell you in the very first time when we saw it, don't worry about it, you're trying to find the midway out of it, right, in here. So you think like, oh, there's a number and I just have to minus 0.2 and then add 0.2, right, our regular way of calculation. And in order for you to get 1.3, you thought like, oh, the mid got to be, yeah, 1.1. So if I add like 0.2, I would go 1.3. So if you had like a 1.1 here minus 0.2, then it won't make it, yeah, to 1.0. So that's why we call this one the added, yeah, added on the bonus and tolerance. And you will be adding away from this, going down each unit, because our tolerance is going with 1 decimal, yeah, so 0.1 decimal. So you're going to go increment of a decimal, yeah, keep going all the way you get to your LMC right there. So you know that the added tolerance go 1 time, 2 times, 3 times from your MMC. And this is what we call it moving away from its maximum material condition towards least material condition, okay? Yeah, be careful with that. So this is just reiterating all of that again, and we're talking about your geometric tolerance going to apply to your feature size at MMC, okay? When you do that, you can be able to use your actual tolerance, okay, and your additional tolerance to give you the combined tolerance, yeah? And we call that the bonus tolerance. This is just reiterating what we have just seen as you move away from your MMC towards LMC. You can also go backwards from LMC to MMC, but at that time you might have to either subtract, yeah? Of course, in this book, they don't go that far. Again, this is just telling you again about the bonus, yeah? Here, this is the middle one is important, right? So bonus tolerance is your additional tolerance. That's what you got to know. Every time we talk about the bonus, it's not just a standard bonus. We're talking about the additional tolerance that you have to give, yeah, for your geometric characteristic that you're controlling in that feature on that part, yeah. And you have to do it because your feature control frame is modified, yeah, to apply to the MMC. So in order for us to account for the changes made to the material, maximum material, yes, condition, then you will have to use more tolerance to it. And if I have to simplify that for you, if you have like a more material, the regular the standard tolerance is not going to work anymore, yeah, because you've got a more material to your feature, so you have to come up with a bonus tolerance to account for that, yeah. So bonus tolerance, again, we're going to count, yeah, from the maximum material condition towards L, yeah, towards least material condition towards L. Make sure you don't get confused, yeah, when you think about your bonus tolerance with your envelope rule, your rule number 1, regular tolerance, yeah, because there are 2 different things, yeah, so therefore do not confuse about that. Because rule 1 is we're just going, I call it regular is because it has its own tolerance, yeah, and it also has its own MMC with that tolerance and the feature control frame, and we're referring to your perfect form, yeah, not the changes or variations or extension, yeah. So this your actual size departs from the MMC, meaning like it changes, yeah. In other words, so size and form variation, you have to change your tolerance with edit or bonus tolerance to account for that. So you can be able to give the permissible range for that change. All right, then the last one is your virtual condition. Yeah, so let's take a look at this, your loss handout. So virtual condition is your theoretical constant boundary. It's not real, it's just virtual, yeah, meaning like we're just doing it theoretically, and we have our boundary, yeah, for your size feature limits, yeah, your MMC or LMC, and you're gonna combine that with your applicable geometric tolerances, okay. And of course, again, so when you read it, you won't get it. We'll have to go into the diagram for you to be able to see it, yeah. So virtual condition, again, will go theoretically, and because all of your size features, they have a virtual condition, yeah. Maximum material condition, we know about that, where your most material, yeah, is being recognized, and you're going to combine that with the rule 1 to get your virtual condition, yeah, for feature of size, and you have no geometric tolerances in there. So let's take a look at it. So here we have no geometric tolerances. See, apply to your external or internal, yeah, features. And we have no, okay, here no geometric tolerance, just a regular 8.0, and you can go all the way to 8.4, 10.4 and 10.8. Then we call that the virtual condition because there's no, yeah, geometric features in it, just a regular. Your MMC is 8.4, so you can add a 0, no geometric tolerance, so you get 8.4. So that's your virtual condition, and that's your external feature results because we're using this, okay. Then internal, yeah, so here internal, you can see this, yeah, feature of sides. Don't, again, some of the students have issue talking feature of size and then they get into confusion. This is a feature and that is a size, okay, that is a size and this is a feature, and it can go from 10.4 to 10.8. That's what it's saying, yeah. So don't worry about the name of it, yes. Internal, inside, we have a feature which is this, we have a size which is that, we have an MMC which is this, yeah, the max, because this is internal, so 10.4 is your MMC. Why? Because you have to leave the most material, which is these are material, yeah, so therefore your whole got to be the least, so you will have the most material on that part, yeah. So you got to at least know that just by looking at it. So therefore your virtual condition is there's no geometric feature tolerance of 0, yeah, so 10.4 you get 10.4, yeah. All right, the next one we're showing, yeah, here external, and this one internal. Now look at this, you have a geometric tolerance because you have a, see, look at this control frame is given to you with the geometric feature 0.2, yeah, where we count, remember the bonus, yeah, bonus going away from MMC, and then we count all the way with it, yeah. So now you got it here, geometric, yes. Virtual condition, we are add it from your MMC, yeah. So 11 internal MMC 10.2, yeah, get the least for internal, then add your geometric, yeah, so we get 10. So that's your virtual condition. Now we come into problem 48 in your textbook. Yeah, so unit 5 is pretty easy problem. So I just want you to go ahead and do it and upload it. Yeah, 3 of your choices. It's not drawing. It would be nice if you do all of them, but it's okay. I have already do this for you in my lecture, so you shouldn't have any kind of issue. Yeah. So some of the students in the first couple of chapters have an issue, but because they're not, I think they're skipping the lecture, so they don't really see the handout or lecture, so they have an issue trying to get the answer because the answers are in the lecture, yeah, also in your handout given to you, that you can be able to do it. So anyway, this is problem number 48 in your handout, yeah, and it's just asking you a few of the questions with this diagram. Oh, what is the MMC? What is the LMC? What is the virtual condition? Yeah, with or without MMC, and with or without a geometric tolerance with it. So you can go and calculate it. Yeah, I'm not going to calculate that for you. This is your homework. For your MMC, you have to look for it. Where is the MMC? Yeah, and we're talking about the mounting holes. Yeah, mounting holes are right there. Yeah, so you know that you're dealing with around here. Yeah, so here is your dimension, and here is your tolerance for this. Yeah, and this we call it the geometric tolerance. Yeah, this is your regular. You will have to start calculating that. Okay, so the mounting holes, yes, it's a hole, so therefore it's an internal. Yeah, and you have your MMC, so you have to go and cut it by minusing from here. Yes, so you have to minus 0.005. This is where you get this. Yeah, so 0.620. You have to add 0.10, not the same. See, tolerance is a little bit different. Completely specify what's the lower and what's the upper limit of it. Sometimes the upper and lower limits are the same value. Yeah, you will get the plus and minus sign with the same value. Sometimes it's different like that. So just pay attention. Yeah. Then let's talk about the LMC, which is the opposite of that. Yeah, you want to leave the least material on your part. Now you're dealing with the outside diameter of the ring. So it goes to outside diameter. So therefore, look at this. Yeah. So you're going to choose the right dimension, which is this guy. Yeah. And then, of course, you have to get rid of this. In order for you to get the LMC outside diameter, we have to leave the least material. So you have to go the maximum of it. Okay. So I see a little typo here. So that's got to be 81103. Okay. That's just a textbook typo, and you can fix that one. And then your virtual condition of the mounting holes is going to give you 0.606. Okay. All you have to do is just add this one, 0.0140. Add to that. Sorry. You have to minus 0.014. Is talking about the mounting hole, so not I was doing LMC. So anyway, so MMC. So MMC, you take the 0.620 and then minus 0.140, your geometric tolerance. So you're going to get the 0.606. And of course, all of them are your basic dimensions because they're written here in the rectangles. Alright, so that's it for your unit 5. So make sure you do your problem 45, 46, 47, 48 for this chapter.